I asked that I speak today because I'm an old man, and I thought if I get the 2 lectures over with, then I'll sleep well tonight and can enjoy tomorrow's lectures. And now, I have had a specific reason for writing this, for doing it. As I say, it was a 3-year effort, and it was a disagreeable effort. It cost me 3 years of real life and another 3 years of anticipated life, I think. But
that just extends your life 3 years.
what?
That extends your life for 3 years because it's very healthy doing those kinds.
You think so? You think so?
Absolutely. We encourage you to do it more.
Okay.
Depends if it works out.
And anyhow, and of course I'm writing with a certain missionary zeal. Namely, I do not like as I said, the geometric Langlands program as it's presented. And I think there should be a theory in which the Hecke operators are, what?
Religious bigotry, is that what you're confessing?
No? You know, I mean, I could make a remark, but you might be out of place. So, what I hoped all the time was to present a theory for the simplest case, GL2 over an elliptic curve. I mean, of course, the rational curve is easier, but GL2 over an elliptic curve, which was convincing. That is, was convincing in the sense that the automorphic Galois group existed. That's one sense. And secondly, that you could consider the possibility, seriously consider the possibility of building a general theory with the same predilections, with the same prejudices, namely a general theory in which you could see explicitly the Hecke operators, and in which you could calculate explicitly the Galois group, the automorphic Galois group. And as I say, I think that I started out this morning and I did the Hecke theory. The Hecke theory is pretty clear, and now I want to explain what the geometric Galois group looks like. And of course, you got the connection with Yang-Mills connections as a supplementary gift. The Yang-Mills connections in this case are just as I say, basically the constant connections on a curve, elliptic curve, and they're more or less that probably for other curves in a certain sense.
So
and
let me ask you one question. So Yang-Mills depends on a choice of metric on the curve, right?
Yeah, well, choose the right metric. I mean, if you want to get a
no, so on the elliptic curve is an obvious choice, but what in general it's going to depend
on what you can do. What I would suggest you do, I haven't done it, is put that metric on the Picard variety or the Jacobian variety and pull it back. I mean, that's the obvious choice. I haven't tried it. I want to say something again about the possibility of generalizing it to an arbitrary curve, arbitrary genus. Now, of course, that's a different matter. But it's clear, if you look at it, it's clear that and an arbitrary group, not just GL2, GLN, but an arbitrary group. And it's clear what is there, if you look at it, is you have the Picard variety as the base, but then you fudge with the Picard variety just a little. Or you have, in the case of GL2 and direct sums, you have what's it called, the factor of the parabolic, and you have 2 pieces in the semi-simple part of the reductive part of the parabolic, and for each of the pieces you have the Picard group. So you basically have a product of Picard groups, more or less, right? It's a little bit like what you did. You have it exactly, but not quite. You have to fudge. So before I go on, I mean, let me just say that how you will think of moving on. I want to talk something about say a little bit of the automorphic Galoisian group in this case. But let's say a little bit, if you're thinking of going on, how am I going to do the general case? So as I observed right? I can't do GLN because I haven't tried yet, but I'm not so sure it would be easy. I cannot tell you, given a vector bundle of dimension n, whether it's decomposable or not. Dimension 2, I can look at it and tell you. But dimension n, I never thought about it, but you need some criteria. In other words, this...
It decomposes in different ways depending on the parabolics, right?
What?
You get different regions where it decomposes differently.
Yeah, it decomposes differently. Different regions, I don't know. They're all mixed up.
No, but you have parabolics. Doesn't each parabolic give you a region in which things decompose according to the parabolic?
Yeah, but if it's not, doesn't look like, if the parabolic group is given to you in advance, then you can tell that it's decomposable. But if I give you a vector bundle, decide, how do you know, for example, that these Tia bundles are not decomposable? I mean, how do you know it?
I want to tell you something.
What?
Not now.
I mean, I find it's a problem. If I apply a Hecke operator to one of these bundles, and then I look at what I get, I say, is it decomposable? Well, since I don't know what the elements of the decomposition are, I can't test it. You know, it may not.
There's an answer in other cases which might apply here.
What's the answer?
What
What is it, a secret?
On the contrary, but it's too complicated to explain.
Okay. In any case, for me, that's a problem. All right. That's the first question, and then the second question is for other groups, right? For other groups. Now, for GLN, if you look at what's in it here, you'll see that you will generally get products of various decomposable things for smaller groups, and the Picard variety itself of the original group will occur just once. But now one can expect that for other groups, which are with other kinds of unipotent elements, and I mean that depends. You saw I wrote down the relevant bundle. It depended upon the fact that GL2 has basically one unipotent element. And that's why the other groups presumably have various kinds of unipotent elements. I'm telling you what I can't do. Who knows? Someone else might be able to do everything. But so you don't know that.
In Mumford's theory, you get parabolics, not unipotent elements that tell you what happens.
Thank you very much. But you know something that, I mean, what I've noticed, which may or may not be correct, is that the notion of a stable bundle does not appear in the Tia classification.
But it does appear in Yang-Mills.
No.
In the Tia Bott paper, they talk about stable bundles.
Yeah, stable, but Tia and Bott, on the other hand, may have been misled by the current fashion for stable bundles. I don't know. In any case, I see, but what I see is that if you look at it properly for a while and think about it, then you might be able to deal with these questions. The fact that maybe there's more than one class corresponding to a Tia class for other groups or for other genera. But I didn't do it. But what I think is that the example of GL2 over an elliptic curve offers an incentive for approaching a general theory.
So the notion of indecomposable is not the same as stable?
No.
Yeah, I know that. I mean, I know that.
What's the difference between them?
Pardon?
What's the difference between them?
I'd have to recall the definition of stable. Do you want me to do that? I mean, decomposable is decomposable. It's a direct sum. Stable means it doesnn't have a certain kind of quotient.
Every subbundle we have an inequality.
Decomposable means literally a direct sum.
Yes.
That's and stable means that you somehow can't break it up into a piece of a quotient when one is high degree and one is low degree.
I see. I see.
And in
I
degree 0
I misunderstood.
coming from in degree 0 stable also means coming from a unitary local.
Right. I see. Okay. I misunderstood.
Okay. Good. So you have nothing to confess or to be up.
And nothing to tell you that you're interested.
Okay. Now, so So that's the last point. I mean, I don't have anything very concrete to suggest, but if I were younger, I would really look at this possibility of creating a general theory and along the lines of what's available for GL2, but for arbitrary genus and arbitrary groups, reductive groups. And if you're really ambitious, you could try to do a theory in which was ramified. Okay. Now, the other thing. So for what I did this morning, which I think was a little bit confused in my exposition, I look at my notes again and it's less confused. I would recommend the written form. And now I just want to go to this question about the automorphic Galoisian group. This is really great chalk. It sticks like paint. Okay, so we write it, and now here I really follow something more or less from a Theobot. So, and you'll see that it's. So they introduce a group which is this. It goes to Z, gamma, and pi 1. M. So M is the elliptic curve or a general a Riemann manifold of genus G. And then they build gamma R, which is equal to R times to Z with gamma, this being gamma. So gamma, what gamma is, I could put a 1 at either end. So gamma is following. You take the fundamental group of the Riemann surface, and you take the Riemann surface and you puncture it, and you take the fundamental group as what is left. And why this works, I don't know. And that's gamma R, and there is a proof in a Theobot that this classifies Yang-Mills connections. And classifies Yang-Mills connections.
And
Now,
in what sense classifies?
what?
What do you mean classify? What is it?
Homomorphism of this thing into a group gives Yang-Mills connections with.
What's the group? Homomorphisms of this into
If I have a G bundle, then into G. It's a remark. I mean,
One way to think of this group also is that you take a line bundle of degree 1 and you remove the 0 set.
yeah, that's the same thing.
That's
Yes.
one bundle and it makes clear.
Yeah. I think that's what they do, right? So, in any case, what the group is very concrete. So this has, in general, it has the 2G generators, AI, BI, and this A2, B2, and so on. And so on. That's equal to J, and J is 1 in Z. So that's not, it's a non-zero element in Z. So this is the group. It can be realized in that way. J is a central element. And so I sort of, and it's a mistake, but I sort of think of following the notation of Whittaker-Watson. So I think of them being those two loops. I think of genus 1. But I'm only can do something in the case of G equal 1, but the definition is relevant in arbitrary genus. So what I say, these represent equivalence classes, so homomorphisms into, now it's better to say homomorphisms into GL, the L group, give you the connections in GL. In other words, in the theory of automorphic forms, homomorphisms of something are into the L group. Well, and that, but they consider GLN, so it doesn't matter. Now, so I haven't really pursued this, but what I want to say is I want to look at the analog for, in our case. Now, basically, I will use the same gamma, but not quite. You know, they do the same thing, except I only want representations of gamma in which the image of all these things is a finite order. So I basically want to introduce a group which is the same as this, except that I impose the condition that each one of these things has an image of finite order. So that's the group. So, and actually it looks like this. I do the projective limit over I. I mean, you can get, I just take a sequence of subgroups so that, to say the group has an image of finite, finite image means that it factors through some gamma ni. Or all elements are finite order, rather. So that's what it is, I guess. And the z is just to accommodate the fact that I'm dealing with things which have a degree. The z measures the degree.
You're making the image finite or the generated finite order? Like
Huh?
full image.
Every element in the image has finite order.
The whole group.
Yeah.
And is this thing here something you replace z with in
It's the thing which it's the analog of gamma.
Ah.
Okay, I take images in GL, which which is still GL2. So the images in GL should parameterize the Hecke eigenfunctions.
I don't think you can keep z as center.
What?
You cannot keep z as center. You need z mod n.
This C is an altogether different thing. In other words, I have the Picard variety. Picard variety is a connected part.
Oh,
Plus, this C is just the disconnected part. Yeah. No, over here I have to get rid of it. In other words, the basic example will be when J is equal to plus or minus 1, right? Yeah, no, I agree. This C, I have to replace this C by some inverse limit of finite quotients. Yeah.
So it's compact.
What?
It's compact.
Well, I mean, inverse limit. How seriously do you take inverse limits? You go to find some finite quotient. So yeah, I mean, it's just inverse limit is just a way of saying I've done it all. Huh? Yeah. All right. So now let's just look. Now all you have to do then is look. I confess it took me a long time just look. So now I have to tell you, if you give me a line bundle, say, what's the corresponding, just a minute, I'm going off the deep end. I said I'm looking at the Hecke eigenfunctions, or the eigenclasses of a GL2. But for a Hecke eigenfunction for GL1 is 2 alpha omega 1, this is the basis, remember, plus 2 beta omega 2 goes to exponential 2 pi I A alpha plus B beta. You will agree we're now down to GL1, and I'm forgetting the disconnectedness of the Picard variety, and so I'm looking at the Jacobian variety, and it's just the elliptic curve itself, and these are the basis of any of L2 basis in any sense, and these are also the eigenvalues of the Hecke eigenfunctions. And there they are, and all you want to do is define them by means of maps of this. So all I have to do is tell you what the image of A1 is and B1 is. And the J doesn't really matter here because it's going to be abelian in the GL1. So, I mean, it's quite clear. I just send A2. What do I do here? I write this alpha beta is equal to M, A, B, right? where A and B are relatively prime. So M and A goes to e to the 2 pi I. A over M. And B goes to e to the 2 pi I. B over M. It's very simple, and it works. All right? Now you so you can, and now if I go up to GL2, it's pretty clear what to do. GL2 is just the direct product of these two things. So now what do I do with the bundles GL2 that aren't decomposable? So I want to see what the correct parameter is for GL2 bundles that are not decomposable. It took me. I'll tell you, and I'm actually rather ashamed to tell you, but I'm going to tell you now. Anyhow, so I'm looking for GL2. That means I only have one A and B. And a typical representation would be, and in this case, if you think of it, if I have a two-dimensional representation and all this is not there, if you look at this equation for not very long, you'll see that J, if it's not 1, which I suppose it's not because the B in case I've just treated, it has to be minus 1. When you look at this, you see it's determined. The determinant is 1, and it's central, so it's and it's not 1. So the kind of representations I have are obvious. Namely, I can send this into A minus A, and it's also obvious that the eigenvalues, if I have an eigenvalue of A, then it's minus that eigenvalue is also an eigenvalue. So, and B has to be, well, it has to have a certain effect on A. It has to change it into its negative. So B would be that. All right? Oh, good. Now, I have, and in fact, that's what it is. And here's what you'll think. It looks a little bit funny, and at least I thought it looked a little bit funny. And what I have too much. If you look, I have too many possibilities. So it's best if you're careful. It's best if you just observe. Well, if A goes, so the eigenvalues of whatever A goes into are of this form, e to the 2 pi I. What did I use here? That's wrong. Let's call this alpha and this alpha. It's beta. And this beta are 2 to the I pi A over M. This is e to the 2 pi I B over M. Right? And the same thing, minus, plus or minus. And this, the eigenvalues are this. It is. I looked at it for a while, and then I just couldn't. It is too much of a choice. I mean, all these things. Some of these things are equivalent, and some some aren't. And how do I tell? So, and the reason I didn't do it, I didn't have the good sense to say, well, look, for all practical purposes, except for this J, this group is a billion, right? And I'm free. It's a fundamental group. And I know something I never quite understood. This is a confession. I tried to learn topology once from a book of Lefschetz. And that book of Lefschetz discouraged me because, as I discovered later, he inserted a lot of unsolved problems into the exercises, and I lost it. So I confess I still have a little trouble with the usual definition of the fundamental group of a surface as a product, because the smart thing to do, for all practical purposes, I can use any basis right? I mean, they're all the same. They're just signs, plus signs that don't matter here. So all I'm do is, if I'm given A and B, I make sure I choose, say, A, so the eigenvalues are right, and B, so it's 1, 1. So I change the coordinates. I replace A and B by better coordinates. And so it took me some time to replace it by better coordinates. In any case, that's about all I think I've said what I had to say, or what I could say, about the possibilities of general theory. This, I think, I've more or less presented clearly it's a very simple proof that, at least for elliptic curve, I really do have the group that represents the non-decomposable line bundles. And I mean, I somehow didn't go back. There's some part that I left out the Jacobian variety. I left out the point. How do you get from this to an eigenfunction of the Hecke operators? Well, these are the two basis elements, and this alpha and beta are just these things. And as we know, the eigenfunctions of the Hecke operators from a previous calculation are just functions like that. So that's all I wanted to say. Thank you very much for listening to me. And as I repeat again, I'm quite pleased with the results. Whether you are or not is, of course, another matter. Thank you very much. Do I have to introduce the next person? No.